Hi everyone, this is Mrs. Jackson. This is Chapter 4, Section 4, Part 2. And in this video, we are going to look at transformations to the reciprocal function. Specifically, we are going to look at translating the reciprocal function as well as stretch and compression. And finally, we'll take a look at reflections. Let's just take a quick peek back at the parent function, that is y equals 1 over x. And the horizontal asymptote is the x-axis. And the equation for the x-axis is y equals 0. And the vertical asymptote is the y-axis. And the equation for the y-axis is x equals 0. Our domain is all real numbers except x cannot equal to 0. And likewise, the range is all real numbers except y cannot equal 0. So hence the asymptotes. So what does it look like when we translate the reciprocal function? So here I have a translated one. And the first thing you're going to want to do is try to see where is that horizontal asymptote and where is the vertical asymptote. So here I could see that my graph is being guided towards y equals 3, but not touching it. And my vertical asymptote is being guided towards x equals 2. I'll put that in orange, but not touching it. So you can clearly see that we've translated our parent function to the right 2 units and up 3. All right, so how does that look in the function itself? Well, first of all, in our particular example here, our horizontal asymptote is going to be y equals 3, and our vertical asymptote is x equals 2 in orange. So if we take a look at the effect on our domain and range, our domain is all real numbers except x cannot equal that 2. And our range is all real numbers, except y is not going to be able to touch that 3. So let's take a look at a generalized function for a translated reciprocal function. As was the case the entire year with all functions, if we change our x dimension, that's responsible for moving left and right. Specifically, if we subtract, we go to the right. If we add, we're going to the left. So if we could just make a note here that this is left-right. And of course, if we add or subtract directly from the output here, in this case with k, that's going to be responsible for translating up-down. So it's extremely consistent on every function we've looked at this year. So in our particular example here, we've shifted up 3 units and we have shifted to the right 2. So I'm just going to put some placeholders here and fill in my numbers. So I went to the right 2 units. That means I am going to subtract 2 from my input variable. And we shifted up 3 units. That means I'm going to add 3 units directly to my output. So if we generalize then, if k is responsible for shifting up or down, then I could generalize and say that my horizontal asymptote is going to be at y equals k. Likewise, if our h variable is responsible for shifting right or left, I could say that my vertical asymptote is going to be x equals h. And if I take that further, then my domain cannot equal that vertical value, that vertical asymptote, and my output cannot equal that horizontal asymptote. And so you can see that it's very evident, both in the graphical form as well as the function form, that we can read translations right off the graph or in the equation itself. Now, how about stretch and compression? The first example we're going to look at is stretch. Now I know that your notes are in black and white format and you can't see these colors. So I did put the parent function in solid and the stretched function in a dash line. Now how would I know if it weren't labeled that this red curve is the parent reciprocal function? Clearly you can see it is a reciprocal function, but I can tell that it's a parent because it's going right through points 1, 1 and points -1, -1. So as soon as I see that, then I know this must be y equals 1 over x, because 1 over 1 would give me an output of 1. So whether or not the parent is labeled, you can always tell whether something's been stretched or compressed if it does not go through that point 1, 1. Now how can I tell if this green dashed reciprocal function is being stretched or compressed? Well, the first thing you're going to do is look to see where it crosses directly on the grid. So I have a point here and I have a point here. This point here is 2.5 on my x variable and 2 on the y. And this point here is 2 on my x variable and 2.5 on my output variable. So if I take a look at a generalized function here, I've got f of x equals some kind of stretch or compression factor over x. Instead of a being equal to 1, it's going to be another value. Now, up until this point, all functions that we've looked at, a is greater than 1 when it's being stretched, and a is less than 1 when I say less than 1, I mean greater than 0 and less than 1. Then we've looked at that as a compression. And there is no difference in the case of the reciprocal function. So how can I actually find a? Well, we always solve for a by plugging in a point. And so if I do that now, if my output, I can use either one of these points. But if I put my output here at 2.5, I'm going to write that as 5/2. And I have some kind of stretch or compression factor, and my 5/2 happens when x equals 2. So if I cross multiply this up here, this 2, in other words, multiply both sides by 2, I get 10 over 2, which just gives me an a of 5. So you could see that a is greater than 1, and therefore our function here is being stretched. Now it's important to note that this stretched reciprocal function has not been translated. So the vertical and horizontal asymptotes are going to remain the same between both the parent and the stretched version. So it's going to be the axes, the x and y axis. So nothing's changed from our excluded domain or range. Okay, let's take a look at an example of compression. Again, I use the dash lines to show the transformed function. And if I didn't tell you that, you could still figure out that this red one here is our parent because it's going through the points 1, 1 and -1, -1. All right, so the blue dashed function is, we're going to look for some kind of points that go right through the grid, and I see I've got one here and here. That point is at 1 and an output of 1/2, and that point right there is an input of 1/2 and an output of 1. And so let's take a look at what value of a will result in these points. So you can use either point that you want to. Our output is 1/2. I'm going to use this first one over in the lower right. My output is 1/2 when my input is 1. And so if I cross multiply, I get a equals 1/2. And that's exactly what we would expect for a function that is being compressed. And so for our dashed line here, I could write that as 1/2 on top here, over x, or I more likely write it as 1 over 2x. Both of these are equivalent functions, and you can see that they are both compressions. And once again, without any translations left or right or up or down, this new transformed function has the same exact asymptotes as the parent, which are the x and y axes. Okay, and finally, let's take a look at reflections to the reciprocal function. So again, here we have our parent, which is in red, and we can tell because of this 1, 1. So I have y equals 1 over x. The transformed function is in blue dashed, and you can look at this in one of two ways. So you could see that this quadrant 1 area here is now over here in quadrant 2, and the parent in quadrant 3 is now symmetric and over here in quadrant 4. So the way we could look at that first is as a reflection over the y-axis. However, because of the symmetric nature of the parent reciprocal function, you could just as easily look at this as a reflection over the x-axis. So either way, you're going to get this blue dashed function here in quadrant 2 and quadrant 4. Now, just as we did with compressed or stretched functions, we're going to look for a point here on our graph. I see one at 1, -1. Or I could look over here at -1, +1 at the output. Either way, if I take a look at this function in blue, I'm going to look at it as some kind of stretch factor. So my output is +1 when my input is -1. So my A is -1 times +1. Therefore, this reflection of our parent is going to be y equals -1 over x. So it's exactly what you would expect, what we've seen with every other function this year, is when that a turns negative, that also means a reflection. So in this short video, we took a look at 3 different ways to transform the parent reciprocal function. We looked at translations, left, right, up, down, and its effect on the equation itself. We looked at stretch and compression and how that affects the function. And finally, reflections. I hope this video helps. Thanks for listening.